But we have a special guest today, and that is Dr. Karl Hausker. He is a senior fellow at the World Resource Institute's climate program, and he leads analysis and modeling of net zero emission pathways and leads work on electricity market design. Dr. Hausker has worked for 3 decades in the field of climate change, energy, and environment in a career that has spanned government, research institutions, NGOs, and consulting. He's also served from 1993 to 1995 as a Deputy Assistant Administrator in the EPA's Policy Office. Previously, he served 6 years as a Chief Economist for the State Energy and Natural Resources Committee. And Karl holds a master's and a PhD in public policy from the University of California, Berkeley, and received his bachelor's in economics from Cornell University. Karl and I were introduced recently, and we decided to put on a webinar based on the IPCC Assessment Reports. They've recently released their Sixth Assessment Report earlier this spring, which is always a vast and expansive undertaking to really read and understand the entire thing, being around 2,000 pages long. So what most people tend to read is the summary. And there's a lot that's talked about in this report about nuclear that's left out of the summary. And Karl's done the great endeavor of really digging into this report. And so we're gonna learn what's in the assessment report about nuclear that's not so much talked about in the summary. Karl, is that a good?
That's a great intro, Matt.
Okay.
Yeah. Yes. Thanks for this opportunity. Hello, everyone. I've met some of you in the past. Great to see you again. I'm going to give a little background on the AR6 process. I'm going to discuss how the mitigation scenarios were depicted in the summary for policymakers, and then do a deep dive into the full report and contrasting what's in the SPM versus the full report, touching on how primary energy demand is dealt with, the overall electricity generation mix, and especially the treatment of nuclear generation. I'll then turn briefly to how these things were also covered in the synthesis report that came out just in March of this year, and then we'll turn to that Q&A. I'll move pretty fast, but the slide deck will be available. So let's get nerdy and wonky and dive in. As many of you know, every IPCC assessment consists of 3 workgroup reports: science, impacts, and mitigation. This latest round did those 3 reports and also integrated 3 special reports, one on oceans, one on climate change and land use, and the special 1.5 degrees pathways report of 2018. I like to think of IPCC reports as 3-layer cakes. As Matt mentioned, the full reports tend to be 2,000 or even up to 3,000 pages long. Each of them has a technical summary, about 80 to 110 pages long. And then there is an SPM, a summary for policymakers, typically 30 to 50 pages. And then at the conclusion of the assessment, there is a synthesis report trying to tie all of it together and boil it down. On this last round, that full report was about 85 pages, and they distilled an SPM of the synthesis report of about 36 pages. As you can imagine, an SPM and a synthesis report is extremely challenging to write. To do that successfully, to boil down all of that, all those scientific findings and analysis. It's also particularly challenging to do the SPM and the synthesis because the full reports are written by the scientists and other experts, but the SPM and synthesis reports have to be agreed to in a process involving all 195 nations that participate in an IPCC. Yet, as Matt noted, the SPM may be the only document that a policymaker or a stakeholder or a journalist will read. So if it's not accurate, then that's a big problem. What I'm going to present today reflects my role as an expert reviewer of the Work Group 3 Mitigation Report and the Synthesis Report. So I've submitted comments on multiple drafts of these documents over the last 2 years, and I've observed the evolution and the process. And overall, I really want to praise AR6. This is a Herculean task, relies on thousands of volunteers. It does provide the most comprehensive and objective assessment of all facets of the climate change problem and of the solutions. My personal view on the mitigation report is that the full report and the technical summary do a great job assessing the scenarios that can limit warming to 1.5 or 2 degrees, get us ultimately to net zero GHG emissions. But the full report conveys some important information and findings that did not make it in to the SPM or into the synthesis report, and the near absence of any reference to nuclear generation is particularly troubling in my view. So let's dive into the sort of the lingo of the mitigation report and talk about mitigation scenarios and illustrative mitigation pathways, or IMPs. The Work Group 3 process examined about 1,200 scenarios, modeling studies from the literature, and projected their warming levels into 8 categories, C1 through C8, depicted over here on the left side of the screen. And we're going to focus, as the report largely does, on the categories C1, C2, C3, which limit warming to 1.5 or 2 degrees. The experts took a look at the 1,200 scenarios, applied some vetting criteria on whether they picked up on historic trends reasonably, if there was sort of near-term plausibility and enough modeling coverage to be able to translate it to a warming projection. And they narrowed those 1,200 down to about 540 scenarios that fell into the C1 through C3 categories. So one depiction of the findings is looking at the median value of these 540 scenarios, or the 25th to 75th quartile range of some indicator, what is energy demand, how much solar is used, how much do building consumption decrease, et cetera, et cetera. So looking at them in kind of a statistical way. And the second way to depict the work of Work Group 3 is to look at the illustrative mitigation pathways. And here, what the IPCC did was look at all of those scenarios and develop several storylines of specific scenarios that they would then call a illustrative pathway. 2 of those we're not going to talk about much. It's what they called current policies, just projecting out, or just moderate actions on top of current policies. The 5 that they picked to illustrate 1.5 and 2 degree pathways are on the right-hand corner here. One fell in the C3 category. They called that gradual strengthening of policies. They had another pathway that emphasized negative emissions, carbon dioxide removal, which was in the C2 category. And then 3 that fell in the C1 category, hitting 1.5 degrees, a very heavy renewables scenario, a very low demand LD scenario, and a scenario that moved quickly to meet very sustainable development indicators, shifting pathways towards sustainable development. So that's the lingo that we're going to deal with here, as then we turn to how they depicted their pathways. They did it 2 ways in the SPM. They did it by looking at total greenhouse gas emissions and then a sectoral breakdown of what's happening to emissions. So over on the right here, you see what probably looks like a typical graph of what we need to do to preserve a safe climate. This may look familiar. On the y-axis here, we have gigatons of CO2, and then we have projections out from 2000 to 2100. And this is just looking at CO2 for a moment. They also have analogous figures for all GHGs, for methane, and N2O. And so what you see here is sort of current policies, business as usual, kind of in the orange categories. But then in these kind of purplish, lavender, bluish categories, these are your 500 or so scenarios that could keep us at 1.5 or 2 degrees. And then the dotted and solid lines are the illustrative mitigation pathways that are within that envelope. And I want to say one thing that I think the IPCC did particularly well is really illustrate the need for negative CO2 emissions as we go over the next 30 and 70 years. We will have to turn CO2 emissions negative through biological or technical means, partly to offset the non-CO2 gases, which are very hard to reduce all the way to zero, partly to offset residual CO2 emissions where we may still be burning some fossil fuels by mid-century, and finally, to compensate for an overshoot of a temperature target of 1.5 or 2 degrees. And we literally will have to take CO2 out of the atmosphere to cool the planet back down to something that we feel is safe. So this is the typical sort of toboggan slide downward we need to get to on CO2 emissions. But of course, it doesn't tell us yet much about what we have to do to get there. For that, the SPM offered a sectoral breakdown of emissions that actually I don't particularly find very helpful, but they depicted one aspect of, again, and this is what's called SPM figure 5, which has about 5 different subcomponents, A, B, C, and D, E, and E. What I'm not going to show is a depiction of the 5 IMPs in one future year and the role of carbon dioxide removal. Instead, I'll show you something that does try to depict what has to happen. It depicts the sectoral contributions in percentage terms to a 100% reduction of all GHGs, that is to say, to get to a net zero GHG in a future year. And what they've done is taken the median values of all the scenarios, put some little whiskers on to depict the interquartile range, and they've shown, okay, buildings have to contribute about, what is this, about 30% of the reductions total. Industry has to contribute another 30 or so percent. Transport has to contribute 14 or 15%. But these are broken out in terms of direct fuel use in the solid bars. I'm sorry, in the slashed bars, and then indirect emissions through the consumption of electricity or other upstream releases. So this starts to sort of depict what we have to do. They also throw in aiming to make land use and land use change in forestry should become a net negative source globally, and also some reductions in the non-CO2 gases. But the real ball game here, as you probably can understand, is this is the energy supply system that, of course, feeds end uses in buildings and industry and transport. And this is where the battle is really going to be won and lost. Can we get this 74% reduction in energy system related emissions by mid-century or so? But how much energy production would have to decrease if we can reduce demand, or what kind of energies we switch to? There's still no real clues here in this sectoral depiction in the SPM. When we turn to the text of the SPM, which is largely section 3, we still don't get too many answers. It describes qualitatively what a net zero CO2 energy system looks like, And these probably all sound familiar. Minimize the use of unabated fossil fuels, apply some carbon capture elsewhere, turn to electricity systems that emit no net zero carbon, electrify as many end uses as possible, develop low or zero carbon energy carriers, such as sustainable biofuels or hydrogen, conserve energy, be really efficient, and apply carbon dioxide removal to counterbalance any remaining emissions. Okay, that's all fairly standard and qualitative. The text in section C starts to present some quantitative results for the 1.5 and 2 degree scenarios that tells us what happens to the energy system. This is sort of a strange mixture of percentage reductions, tons of reductions, and loading on more qualitative text to the SPM. They give us a lot of detail on how coal and oil and gas must decrease in percentage terms by 2050, providing an even more detail on the interquartile ranges of the mitigation scenarios. And then they throw some numbers out of the cumulative gigatons of CDR we need from bioenergy with CCS, direct air capture with CCS, reductions in land use forestry change, or sometimes called AFLU. But we have no sense of the time pattern of those reductions, but we know the gigatons cumulative. They throw out some numbers on the methane reductions from the fossil fuel sector, reductions from, on again, sectoral basis discussions, and a section on how we can achieve a lot by demand side mitigation in general across all sectors. Impressive numbers of 40 to 70% of mitigation could be achieved on the demand side. But after we read all of this and look at the figures, we're still left asking, what does the energy system look like by 2030 on an interim basis, or by 2050 when we're trying to get to net zero CO2 or even net zero total greenhouse gases? What happens to the demand for primary energy? What are the energy supplies that replace all that coal and oil and gas that are going to be decreasing rapidly? This section ends with a figure called SPM 7 that I'm not going to blow up for you. Don't try to strain your eyes reading this, but it's called an overview of mitigation options and estimates of ranges of costs and potentials. But to me, it kind of comes across as a laundry list of options, some tons by 2030 and some cost per ton. So there's a group of energy options, and here's nuclear energy. It makes a cameo appearance in SPM, shows that you can get maybe a gigaton by 2030, maybe a little bit of low-cost blue bar and higher-cost deep red bar. Here's some AFLU options. Here's some building options. Here's some transport options. Here's some industrial options. But it's just a laundry list. The text warns us that these tons are not additive. They're not part of a particular scenario or illustrative mitigation pathway. It's just a laundry list of tons by 2030, which is really a short-term focus when so much of the work group not only looks at what's possible by 2030, but what's possible by 2050 and beyond as well. So after staring at this laundry list for a while, one's still left asking, what does the energy system really look like in the mitigation scenarios by 2030, by 2050? What's the total demand for primary energy? What are the supplies that replace coal and oil and gas? To answer that, to get some sense of that, you have to turn to the full report. And again, don't strain your eyes on this table yet. I'm going to zoom in on some key charts. But the Workgroup 3 technical summary and also deeper in the report gives a table with global indicators on the 1.5 and 2 degree scenarios that tells us really what's happening in the energy system. Some of these numbers, interestingly, are pulled out in the SPM, so we know where they came from. So let's zoom in on these global indicators and look at what happens to coal and oil and gas. The table has some global indicators for the scenarios, kind of moving left to right, the 1.5 degree scenarios out to the 2 degree scenarios. So things get a little less stringent as we move to from left to right. And here's where we can find those coal numbers in the SPM. the change in primary energy use from coal for 2030, for 2050 relative to 2019, roughly current levels. There's that 95% drop in coal with an interquartile range of 80 to 100 in the most stringent 1.5 degree scenarios. And here's your drop in oil, similarly by 2050, 60%, and your drop in natural gas use. Again, intuitively plausible, as you need to reduce your most carbon intensive fossil fuel most aggressively. And finally, if we scroll down in that table, we can finally find out what's replacing all of that coal and oil and gas. And so this part of this key table, TS2, starting at the bottom here, says what happens to the primary energy from the non-biomass renewables, solar, wind, and hydro. And we see very rapid growth by 2030 and by 2050 over current levels in this 1.5 degree, toughest scenario. We also find that modern biomass, dedicated crops and improved techniques for biomass also grows rapidly by 2030 by 75% as a median value by 2030, and by almost 300% by 2050, which raises some sustainability issues in terms of harvesting all that biomass and competition for food and biodiversity preservation. As some of you may know, WRI has some very strong views on sustainable biomass use. And finally, at the initial rows of this chart, we see a role for nuclear generation. Median value has to grow by 40% by 2030 and nearly double by 90% by 2050, with some very large interquartile ranges here too on the role for nuclear in these mitigation scenarios. Typically slower growth as you move left to right, but again, very significant growth. So this table gives us a very useful depiction of the magnitude and speed of the needed changes in fossil and non-fossil energy sources as we go across the next 30 years. Very interesting. A comparable table like this appeared in the SPM of the 1.5 degrees report 5 years ago. I asked myself, why didn't this table appear this time around? Why would you not want to provide the key growth numbers for the non-fossil sources? But you can't find them in the table or the text of the SPM. Another depiction, or actually, that was talking in terms of primary energy use, and that's where I'll just stop for a second here. I moved through a lot of material here. This is primary energy use, what happens downward on coal, oil, and gas, upward on renewables, biomass, and nuclear. Let me just pause for any clarifying questions there.
So we had a few questions that kind of popped up as we were going along. I think I'll maybe start with Emma's. Emma's talking about some of the earlier charts about what the input from different countries and what ends regarding the input of different countries and what actually ends up in the policy reports. Mm-hmm. Emma, do you want to ask this question, or do you want me to just read what you wrote?
Sure, I can just
go ahead, Emma.
Good to see you. Hi. Yeah, glad that you're giving this presentation. I appreciate it. I just, you mentioned that, what ultimately ended up in the policymakers report does not give credit to nuclear as being part of the ultimate solution to mitigating climate change impacts. And I was wondering, is that process public? Is the process of how countries have input into what ultimately makes it into the policymakers report, is that publicly known? Or is that something that's kind of, debated internally and then you just see the final product?
Yeah, it's kind of in between in the sense of the in-person meetings that happened over the course of 2 weeks at the end of Work Group 3 process and then at the end of the synthesis report were not open to the public, but some journalists did cover them. And I have a point on that toward the end of the presentation and a link that you can go to find some journalistic coverage of how and what happened. So let me hold that for now, and let's return to that.
Okay, awesome. Thank you.
We have another question from Chris regarding the earlier charts of what energy sources need to go and what should stay. So I just posted his question into the chat, but Chris, if you want to hop on and kind of give us an idea of what you're aiming for on this question, feel free to.
I'm just thinking that, I mean, for several years, I've thought like the Trillion Tree Program, most of what that's going to do is replace half or 2/3 of the plankton that we've lost. I see it as a net loss if we plant 1 trillion trees. I'm just curious if there's some plans involved or expectations that we need to preserve what nature's already doing, what it's been doing for thousands of years, and see if we can enhance that back to levels like plankton in the oceans or whatever else. To I think that will do as much or possibly more than our direct efforts as humans through our industry and such.
Mm-hmm. I don't have a lot of deep expertise on the biological carbon dioxide removal that you're alluding to, but if you look at this slide, mm-hmm. The LULUCF contribution right now, land use and land use change is a net emitter to the atmosphere because of loss of plankton, deforestation, yes, agricultural techniques. I forget, I think we're, it's got to be probably on the order of 5 or 10 gigatons. I have an appendix slide on that. And our mitigation scenarios generally project that we can turn that around with tree planting, with ag practices, with blue carbon from the ocean, et cetera. So it is definitely part of the scenarios. I'm focusing almost entirely at this talk on the energy sector.
Oh, sure. Okay, thanks.
So let me move on. We can come back to other questions. So let's turn to depictions of the electricity generation mix. As I'm sure all of you know, to meet our 1.5 or 2 degree targets, electricity becomes the key replacement for fossil fuels. We're electrifying end uses in multiple ways. We need to produce hydrogen and other low carbon fuels, and we'll probably need electricity to drive technological CDR. So again, this is absolutely critical to make a lot of zero carbon electricity, expand our grids, but also keep them reliable and affordable. So one would think you'd want a lot of attention on the electricity generation mix. How must it change? But interestingly, the SPM has no quantitative depictions of the mix of electricity generation sources. It does note in the text that we've had large decreases in solar and wind costs over the past decade. It talks about how grids with high penetration of solar and wind are becoming increasingly viable. And as I'm sure as you know, there are plenty of advocates out there who are advocating for 100% renewable grids, complemented by storage and demand-side management. Well, finally, if we leave the SPM and dig into Chapter 6, there's a nice figure that has depictions of the generation mix. And on the next slide, you'll see that the AR6 scenarios are generally consistent with what I would call a mainstream conclusion that solar and wind can grow to be more than half of the generation mix, maybe up to 80%. But we need to complement heavy and solar wind grids with clean, firm power like hydro, geothermal, nuclear, and CCS. And we can see that when we turn to Chapter 6, and it has depictions of the generation mix for the 1.5 and 2 degree scenarios. So here we have three figures of 3 sources. On the vertical axis, we have the share of total generation and how it changes over the next 30 years. We have that for solar and wind, we have that for CCS, and we have that for nuclear. And these are clusters of bars for the C1 C2 and C3, and I think actually this C4 categories. So what we see here is current solar and wind about 10% of total generation globally, growing over the next 3 decades. The median value for a C1 or a C2 or C3 is right in the slots here, and then here's an interquartile range, 25th to 75th percentile of where these scenarios come out. And by 2050, as you can see, most of the scenarios have solar and wind growing to be 50, 60, 70% of global generation, but never really exceeding about 80%. CCS, which I believe this is a combination of both CCS on fossil generation and bioenergy with CCS. I believe it's both. Right now, this doesn't exist. We just have a few pilots currently, but it's very promising. And the mitigation scenarios show it growing to maybe 5 or 10% of total generation as a median value, but also with some upper ranges for a good chunk of these scenarios. And finally, nuclear. Currently, it provides about 10% of global generation, a firm zero carbon electricity source. And interestingly, the mitigation scenarios in terms of a median value generally have that holding roughly steady at 10% of global generation. But again, with some scenarios showing it expanding up to 15 or 20% of total global generation. But it's really important to keep in mind that even if nuclear stays at roughly 10% of total generation, in absolute terms, the total terawatt hours we will be producing by 2050 will probably roughly double in the 1.5 degree scenarios or even grow further. So if nuclear even just stays at 10% of total generation, it has to double in absolute terms according to the IPCC analysis. There's a second way to look at the depiction of electric generation mix. There's an interesting figure in Chapter 3 that shows investment needs. I'm going to move quickly here because I see time. I want to save plenty of time for discussion. In Chapter 3, you have a nice depiction of investment needs. Billions of dollars of investment, annual average over the next 30 years on the y-axis. And on the x-axis, we have different key components of the electricity system: solar, wind, storage, transmission and distribution investments, nuclear, hydro, bioenergy, geothermal, and even a little still building some fossil plants. And what this chart shows us is that, not surprisingly, solar and wind garner a lot of investment in these scenarios, $300 to $450 billion a year each over the next 30 years, annual average. Storage is emerging as an important complement to wind and solar, as you all know, maybe garnering $100 to $200 billion a year, again, across the C1, C2, and C3 mitigation scenarios here. But nuclear and hydro also would require over $100 billion of investment annual average to meet these mitigation scenarios. I don't think CCS is depicted on this chart. I need to dig a little deeper on that. Kind of interesting that transmission and investment is the largest single category. As we electrify the economy, as we produce electricity for producing hydrogen or direct air capture, whatever, we're going to have to build out the T&D system massively at $600 to $800 billion per year investment. So again, this is another sign that nuclear is part of the mix here. And again, complementing what is likely to become a heavy solar and wind system. I'm not going to read this, but I'm just going to tell you that there is a box in Chapter 6, box 6.8, that talks about whether we can go to 100% renewables in a net zero energy system. And it presents many cautions And I think that's important to keep in mind also. And now kind of the coup de grace. Sadly, in my view, nuclear generation was almost erased from the summary for policymakers and the synthesis report. Throughout the Work Group 3 technical summary and the full report, nuclear is on what I call the short list of 4 low or no carbon electricity technologies. And here's an example of one quote. Nearly all electricity in pathways limiting warming to 2 or 1.5 degrees has different shares across pathways of nuclear, biomass, the non-biomass renewables, solar, wind, hydro, and fossil fuels in combination with CCS. But when you turn to the SPM, it truncates this list. It deletes nuclear and deletes biomass too, and says, in these global model pathways, almost all electricity is supplied from zero low carbon sources, such as renewables or fossil fuels. So the word nuclear barely appears in the SPM. We saw it once in that laundry list figure, SPM 7, that I showed you earlier, where it just gets a little line and a little bar. And it appears in the text once in a negative reference to nuclear's, quote, high upfront costs, unquote. So given the substantial role that I just documented the nuclear plays in the Work Group 3 1.5 and 2 degree scenarios, why is it barely mentioned in the SPM? We can contrast it to the SPM of the SR 1.5 report, where it's referred to directly, explicitly. We can go back to 2014 and look at the Fifth Assessment Report and look at the Work Group 3 SPM. It specifically lists nuclear among the other zero carbon sources of electricity. So we're left to ask why? Why was it virtually erased? Well, some countries objected to it being in the SPM, and that was a consensus. You have to have all countries agree to what gets into the SPM. And I've provided a link here to what Emma's question was about. The IISD Earth Negotiations Bulletin provides coverage of these proceedings. And you'll read there that Germany and a couple of other European countries really were pushing to limit any reference to nuclear generation in the SPM. Again, in my view, that's unfortunate and frankly distorts the findings of the full Work Group 3 report. Real quickly, I'm sad to say that the synthesis report, that 80 pages plus the SPM of the synthesis report, just repeats the same omissions in the Work Group 3 SPM. The figures are basically the same. You have your GHGs, you have your sectoral breakdown. The laundry list of options appears again, and it's kind of smooshed together with some adaptation options. You can feel free to look at this at your leisure, but there's nothing in the synthesis report on what happens to energy demand, what the energy mix looks like in the pathways, and what the electricity generation mix looks like, and no reference to nuclear beyond a slight appearance on a laundry list. So to sum up, the full report, the technical summary, provide this comprehensive look, including a balanced objective treatment of the role of renewables, CCS, nuclear and other energy sources. It does provide some caveats on the use of bioenergy, which I think are really important. And the information and findings on the scenarios that did not make it into the Work Group 3 summary, nor into the synthesis report, are a lack of good, clear quantitative depictions of the mitigation scenarios, lack of depictions of primary energy decreases by 2030, which I haven't covered today in the interest of time, but in some of the IMPs, primary energy use drops dramatically. No clear quantitative descriptions of the electricity generation mix, and a near complete absence of any reference to the role of nuclear in these scenarios. As many of you know, if you look instead at what governments are actually planning to do, you'll find plenty of governments not only planning to use CCS, but also planning to expand their nuclear generation or at least maintain it. You look at 5 of the G7 countries, they have nuclear in their long-term plans submitted to the UNFCCC. 9 of the G20 countries have nuclear in their LTS, including China, and 5 additional G20 countries that have not submitted an LTS yet to the climate convention. They have nuclear plants under construction or are planned. And again, thank you all for attending, and happy to have follow-up conversations with you all.
Thanks for your time. Thank you,
Karl.
You bet.